Okay, according to my record, we are all here, except for Tyler, who I knew wasn't going to be here. Christy has withdrawn from school, so she's not in the class anymore. So, we'll finish talking about planetary motion and then review for the exam, because we have an exam on Monday. Yay! Okay, so we were talking about planetary motion at the end of last class period, so we'll continue with the planetary motion. That's all we have left for what's going to be on the exam. The ancient Greeks, which is where we have our foundation of astronomy, had a geocentric view. Now it's important, especially we have quite a diversity of different continents represented here, and it's important to understand that what we teach is a Eurocentric view. That is, the information that we have in the United States came culturally from what they had in Great Britain and Europe in general, and that came from other avenues. So there is, in our understanding of science, the influences of the ancient Greeks, the ancient Arabic scholars, but not so much things like the Chinese scholars or African or South American scholars. So there was work done in those cultures as well. And there's a fair amount of documentation of a lot of advanced work done in Chinese culture specifically, but it's not part of the background of American culture and the knowledge that has come. So that's why we start with the Greeks here, because that's where our background information comes from. So like if I was teaching this class in China, we'd probably have a different history of astronomy going on here. So the ancient Greeks, we're talking people like Plato and Socrates and Eratosthenes, they tended to believe that the sun, the moon, and the stars and the planets all orbit around the sun. Now orbit around the earth. Wow. I screwed that up because I was thinking ahead. We say that, but there were people back contemporary with, Aristotle, who believed that the sun was the center rather than the earth. Right? So we talk about Copernicus being the person who came up with the idea the sun is the center of the solar system rather than the earth. He was just the last person before people started accepting it. So they tended to believe in a geocentric model, a model with the earth at the center. And the reasons for that were pretty simple. You stand here on earth and you feel pretty stationary, unless there's an earthquake, right? So they felt that the earth must be stationary because they didn't feel it move. But of course we've learned. Do you feel velocity? No. What do you feel? Acceleration. So if you don't feel the motion, that just means you don't have a very big acceleration. Not that you're not moving. And in fact, as we understand things now, the earth is rotating and we're flying very quickly around the circle, and the earth is orbiting the sun. We're flying really, really quickly around the sun. So there's a lot of motion going on. But back then they didn't understand that, and it didn't seem to make sense to them that the earth could be moving since they didn't feel it. And also they didn't observe what we call parallax. Parallax is the fact that if I look at, let's see, Daisy right now, I see Daisy just to the right of the chair in the back row. But of course, if I move over here, now I see her well to the left of that same chair. Of course, Daisy didn't move, I moved. But her appearance with respect to something behind her appeared to change its location based on my motion. That's the idea of parallax. If you've ever looked at a little analog meter, a meter that has a line that goes up and down, a little indicator, the fine ones have a mirror behind them. And that mirror isn't to look pretty, it's so you align your eye up so you see the reflection on itself so that you don't have a parallax problem with misreading it. So that was the reason they believed the earth was stationary. Now, just last month, I read some guy's diatribe about how we scientists are just lying to everybody, and it's self-evident that the earth is flat and not rotating. And he had lots of really silly things, like when NASA takes a picture of something, it's usually a composite image. What does it mean for it to be a composite image? Yeah, they took multiple images and they sewed them together, as they say, to make one complete image that's bigger than each of the little individual ones. Why do they do that? So they can have higher resolution. You know, their camera with higher resolution, you can only see so much, and put them all together and have a bigger, higher resolution picture. Well, these people said composite image means it's an artist's rendering. And so what they did is they said, here's what we think it would have looked like. Okay, that's completely misunderstanding the process. And then they said that, you know, there's no actual picture taken of the Earth that shows the curvature of the surface. They have lots of things that don't make sense. The biggest one that made me laugh, though, was their statement that if the Earth was really spinning, as we would have you believe, we scientists, then you should feel that wind blowing in your face incredibly fast. Well, why don't we feel that wind blowing in our faces if we're actually rotating? Yeah, the wind is moving with us. The wind is also moving around in a circle. The air isn't just staying stationary while we spin. And the same thing is true of the water. And in fact, you know, we have tidal pull, gravitational pull between the moon and the Earth. And we already saw the force of gravitation, Newton's universal law of gravitation. Force of gravity is a constant, mass 1, mass 2, over the separation squared. And so, if you take the Earth and you have the moon out here, and if I just take a little piece of the Earth, and I take a little piece of the Earth here and a little equal-sized piece of the Earth here, which one is going to be pulled more strongly by the moon? The one closest. Because it's an inverse square, that is, the force is proportional to 1 over the distance squared. The closer one is pulled more. And so because this one is pulled more, the one that's closer, things that can move tend to get distended out that way. What can move? Largely water. So the water gets pulled out and is closer to the moon on the side that's closest to the moon. Well, on the far side, it's not getting pulled as hard as the rest of the Earth, and so it also bulges out. So we have tidal bulges that are caused by the gravitation of the moon, one on the side the moon is facing and one on the opposite side. So any time there are 2 points that have high tides. But it's more complicated. The Earth is not just stationary, it's orbiting around the sun and rotating. So the Earth is going like that. Well, you have a high tide caused by the gravitational pull of the moon, but the Earth is rotating, the water is rotating with the Earth. So what happens to that raised up water? If it's rotating with the Earth, it doesn't stay here. Where does it go? It's going to move ahead. So the high tide actually pulls up here about 5 degrees ahead of the moon because of the Earth rotating and the water being pulled with the Earth. And so these high tides are a little ahead of the moon, and because of gravity, that gives the gravitational force between the Earth and the moon a little bit of a forward tug. Well, if I have a little bit of a forward tug, that's a little bit of the force that's not perpendicular to the motion. It's going to speed up the moon. Now, as the moon speeds up, things get more complicated. It actually speeds up and moves farther away from the Earth and slows back down. But the moon is slowly moving away from the Earth, a distance of about 1/4 inch a year, because of this action, because of the Earth's rotation. Right? There's a lot of experiments that we can run to give evidence for the Earth rotating. Now, looking at the scientific method, because that's a big part of our test, approximately 16% of the test is scientific method, somewhere in that bar, 15%, I don't know. So with the scientific method, when do we prove something right? Never. You never prove something right. So we cannot, by scientific standard, prove that the Earth is rotating and going around the sun. But we can disprove things. So we can take the theory that the Earth is stationary, and it makes predictions, and we can do experiments to test the predictions of a stationary Earth, and those are very easily and readily disproven. So we can disprove the hypothesis of a stationary Earth. We can disprove the hypothesis of a flat Earth. But we cannot disprove, at least yet, the hypothesis that the Earth is spinning and rotating around the sun. And so we've gotten to the point where we have a really strong faith in that. Now let's look a little at the history here. With the geocentric view, the ancient Greeks noticed that some objects appeared to move every day in the sky. They'd be just a little bit farther, I think it's east. Except there'd be a short period of time when they would move back west, and then they would go east again. So they called these things wanderers, or in Greek, the word for wanderer was planet. So the planets were the things that they saw moving against the backdrop of the stars. The stars appeared to be stationary, never moving with respect to each other, but the planets moved with respect to the stars, and that's how they got their name. Now, this retrograde motion is the fact that they appeared to go backward a little bit. So, first Aristotle came up with a theory that said that all of the planets are on spheres orbiting around the Earth. Now, that didn't work. He had to make two exceptions. The two exceptions were Mercury and Venus. Why? Because Mercury never gets more than about 25 degrees above the horizon, and Venus never gets more than about 49 degrees above the horizon. Pretty good evidence that those are not doing circles around the Earth. And so the model actually had a line coming out to hit the sun. So here's the sun here. And then it had Mercury and Venus doing little circles that were pinned on the line I drew. So they were doing circles on the line connecting the Earth to the sun. All the rest of the planets were doing what's depicted here, doing circles around the Earth, but then little circles around that. I always think of this, and I go back to the song, wheeling a wheel, way in the middle of the air. Easy, so I had a solo in that, but my solo was 2 words. Actually, it was 3. So you saw that wheel. So that's 4. So you saw that wheel. That was my solo. Anyway, so this had the planets doing these little loopy-loop things, and they would be going backward, having the retrograde motion on these parts of their orbits. Now, Ptolemy was the one who came with that idea of the little loops. And so Ptolemy modified Aristotle's view. Now, Aristotle came up with his model before Christ. And Ptolemy came up with his variation before Christ. Like 300 years before Christ was born. And that model was the dominant model for about 2,000 years until we were into the ballpark of the 1500s, 1600s, 1700s. That's the ballpark where people's opinions started changing. Why did they believe this model? Now, a model, that is a framework for helping us understand how something works. It doesn't have to be real. So now Aristotle's model had crystal spheres. Why crystal? Because he considered crystal the perfect material. Why spheres? Because he considered spheres the perfect shape. And so it made sense. Everything out there, he said, was perfect. And so you had the perfect material and the perfect shape, and the planets were going around. Ptolemy made his modifications, and it predicted the positions of the planets pretty darn accurately. For 2,000 years, people used that to predict where the planets would be. I am not going fast. Here's just a picture to illustrate how you have the retrograde motion, because if you look at Mars from Earth, as the Earth moves, when we're lined up with Mars, the Earth is moving faster, and so the angles appear to change. So with a heliocentric view, that is with the Earth orbiting the Sun, retrograde motion is much easier to explain. It doesn't take the complicated loopy-loopy things. And so Copernicus is the person who made famous the idea of, no, it's just the Earth and the other planets going around the sun. But there's interesting names here like Tycho Brahe and Johannes Kepler. I hope to figure out at some point, well, actually, Tycho Brahe was in Wien, Norway, and my ancestors are from Wien, Denmark, so probably not the same place, but I'll have to look back at history because borders have moved. Tycho Brahe is a very interesting person. He had the world's most awesome observatory at the time because he had noticed something unique. We talk about religion and science a lot, at least I do, and oftentimes we talk about those in the context of, okay, religion says that Earth was created, well, that life on Earth was created in 6 days, and the seventh day the Lord rested. That's why we're Seventh-day Adventists, right? But science takes the view that there is no God, or if there is a God, he's not active in the earth. Everything can be explained without God or miracles. And so they come up with a completely different story for how life evolved. And we talk about the two being in disagreement. Well, here is a case of the disagreements between science and religion that we can look back at with the benefit of hindsight. The Catholic Church, which of course would have been the dominant religion, the Christian religion, they took Aristotle's idea that everything out there is perfect, and they said, yeah, that's right, because out there is heaven. I mean, the heavens declare the glory of God. What more do we need to say? That's where the perfection is out there. And so, of course, it's perfect, but if things are perfect, they shouldn't be changing. Because how do you take something that's perfect and improve on it? You can't, right? And so if you make a change, either it wasn't perfect or it no longer is perfect. So the Catholics had this view that everything out there is unchanging and perfect, and sin is here on earth. Now, if you look at the surface of the moon, you can see the surface of the moon is not perfect, right? It's got marks on it and stuff. They say, oh, that makes sense, because the earth here with our sin is imperfect, and our imperfection affects the things close to us. So the moon is basically getting sprayed with some of our imperfections. Well, Tycho Brahe, when he was studying the skies, he saw a brand new star that had never been seen before. And after a couple months, it faded away. So it was known as Tycho's nova meaning new, and he became super famous. So the king of Denmark set him up with his own observatory because he was like the super famous astronomer for seeing something new occur in the skies. That would be something that would be denied by the view that everything out there is perfect. Now, once again, from hindsight, looking at Chinese records, Chinese astronomers had observed such events long before Tycho Brahe observed his. But, like I said, it's European history is what we generally work with. So, he didn't have a telescope. So he had the world's greatest observatory, and the picture comes after this. Now, I just have to put this in. It's not really beneficial knowledge, but it's cool knowledge. Tycho Brahe, if you look at this picture carefully, you can see that he has something funky going on with his nose here. And that there, my friends, is what we all need to do to look at our best. You accessorize. He got in a duel when he was in college, and he most clearly lost the duel because he had his nose shot off. And so instead of doing like I would do, try to make some skin tone thing to make it look like it was normal, he had silver and gold prosthetic pieces to put in there. It's like the precursor of people who have, studs in their noses and whatnot. Now, my question is, what do you suppose this duel was over? Let's see. I haven't opened it up for answers yet. I'm sorry. Now you can answer. Colby? No clicker? Okay, there we go. All right. So we had the answers 2, 1, 1, 4, 0. There are 5 men here. I'm guessing all but one of those men answered a woman. Because that was my first guess, but it was not right. It also wasn't a man. It wasn't over who was wealthier. It wasn't over who was more handsome. How did 2 people actually get the right answer? It was over who was a better mathematician. None of this foolish, okay, pencils ready, here's the problem and solve it, and we'll see who's a better mathematician. No, we settle our math problems with guns. He was a colorful character. Speaking of colorful, here's what his observatory looked like with redone colors. He had this quadrant, and when you look at this, he is in here. Where do you suppose Tycho is in this picture? This is Tycho right here. He's sitting in a chair that's movable, and he has a sight to sight up through the window. So, draw a straight line on this. He's sighting through this window, and he says, okay, I see it at this angle now. And his scribe is down here taking data. So there's the scribe. What does that make this dude? I don't know, some kind of helper. Rumor has it that he had a dwarf who lived there in his observatory who slept under the table and would eat table scraps and keep him amused. Like I said, interesting guy. And of course, he has all these beautiful pictures. But the main thing about the observatory is looking through a hole in the wall and carefully measuring the time and the angles when he saw things pass. And so Tycho took very good data of the positions of the planets and different objects. And he was trying to make himself a new model to replace the Aristotelian model. Well, he died. He died under questionable circumstances. He was at a banquet with the king. He collapsed, went home, and something like 8 or 9 days later died. And on those days between when he collapsed and when he died, he specified that he wanted his new lab helper, Johannes Kepler, to take over. Now, Johannes Kepler himself is a somewhat interesting story. He went to university. He got a job as a teacher. In the first year, he had students. In the second year, he had none. Which would suggest maybe he was harder than me. So he did some things to show some clear intelligence, some really interesting observations about geometric shapes. And so Tycho hired him to come be a person who worked in his lab, and he set him up to be next. Now, when Tycho died, his family was a wealthy family, and the family came to collect their stuff. But Tycho had said it should go to Johannes Kepler. And so they had a little bit of a legal battle, and in the end, everything went to Tycho's family, but Johannes just kept the data. He didn't give them the data, because that was the thing that was really valuable to him. And analyzing the data that Tycho Brahe had measured, Johannes Kepler noticed some patterns, right? The clear intelligence once again. And so we have 3 laws, Kepler's laws, to define planetary motion. And Kepler's first law is that the planets orbit the sun in ellipses with the sun at one of the focal points. Now, what's an ellipse? An ellipse is an elongated circle. So instead of having the center of a circle, you have what we call 2 focuses. And if you ever get stranded on a desert island and for some reason you need to make an ellipse, you can do it. All you need to do is pound 2 stakes in the ground and weave yourself some rope that's longer than the distance between those 2 stakes. And then you just walk around and keep that rope tight with one end tied to one stake and one end tied to the other, and your foot keeping it tight, and the shape your foot traces out, that's going to be an ellipse. Very easy to make an ellipse, right? String and 2 thumbtacks and a pencil. The planets do that with the sun at one of the two focal points. The other focal point is just empty. So that was his first observation. This is just another statement there of the first one. Actually, no, it's the second one. The second one was that the planets move faster when they're closer to the sun and slower when they're farther away. So this here is like day 1 of the month and day 30 of the month, day 1 of the month and day 30 of the month. Right? Bigger distance going from day 1 to day 30 when it's close to the sun, smaller distance when it's farther. But the area that is swept out by the line connecting the sun to the planet is the same for each month. So like if we're in astronomy class, that's an important thing. The area is the same for each month. But still the bottom line important thing is a planet goes fastest when it's closest to the sun, slowest when it's farthest away from the sun. So the Earth is not doing a perfectly circular orbit, it's doing an elliptical orbit. Which means when we're closest to the sun, which is about January 4, we're going the fastest. When we're farthest from the sun, which is about July 4, we're going the slowest. So we speed up and slow down just a little. So that's Kepler's second law. And the third law relates how long a year is to how far it is from the sun. The equation says that the period, which is the time to do one orbit around the sun, what we call a year, squared, is proportional to, that thing means proportional, the average distance from the sun cubed. So what that says is things that are closer to the sun have a shorter year. Things that are farther from the sun have a longer year, and it gives you the actual way to calculate these. So we could say like the period for any planet divided by the period for Earth, which is 1 year, squared, is equal to the average distance between the sun and that same planet divided by the average distance between the sun and the Earth cubed. So it gives us a nice, easy comparison. We call the distance between the Earth and the sun an astronomical unit. And of course, the time for one rotation we call a year. So you can just put, the period in years squared, well, I don't even need to put p anymore. The period in years squared is equal to the radius in astronomical units cubed. That's a true relationship. And that is Kepler's third law. But where did Kepler get these laws? He got them from looking at data and finding patterns. Is that based on a scientific idea? He took scientific data, but then his idea, hypothesis so to speak, was non-scientific because he didn't have any scientific reasons for these patterns. They were just answers he came up with. These would explain it, but no reason why. So it's not really a scientific hypothesis. It doesn't make scientists feel very good. Well, that's where we enter Sir Isaac Newton again. Sir Isaac Newton, okay, we will have this question, but it's not what I want to do right now, so I'm not going to talk about it. Sir Isaac Newton, with his law of universal gravitation and his calculus and his second law of motion, was able to give a physics reason for Kepler's laws. So Newton, who came about 100 years after, I think it's about 100 years after Kepler. I didn't look at the history or the timeline. But Newton, who came after Kepler, then gave a scientific reason for it. Then we have a scientific hypothesis, and we can all feel good because we have a reason for it and not just, here it is. So that is our planetary motion piece. So now, I don't know how many questions. I didn't remember having this question here. And then we'll review. So 3 equal masses are located as shown. What is the direction of the total force acting on M2? So these are equal masses. If I add up all of the forces on M2 due to gravity, what do I get? Do I get something that's to the left, to the right, a total of 0, or it's impossible to determine. Okay, that's very impressive, actually. Very impressive, except for that it didn't stop pulling. There we go. 7-1. 7 people said to the left. Andrew, you're the first one who said to the left. Why did you say that?
Well, if it's gravity, the closer it is, the more pull it would have.
Right. Since the masses are the same in all cases, then the GM1, M2 is just GM squared for all of them. And it's just the 1 over R squared that's going to be different. Since this is closer, that's the bigger force. That one's farther away, it's the smaller force. And so we add those together. The net force, when we add those two together, is going to be this, that. So the net force is going to be like that. I think I have, oh yeah, I do remember this now. So this is just a restatement of how we answered that. Since we've already answered it, we don't need to go through that. The moon. So we have the Earth orbiting around the sun. The moon is orbiting around the Earth. Why does the moon have phases like a full moon, a new moon, and so on? Because the moon is reflecting sunlight. It's not making its own light, it's reflecting sunlight. And so if the sun is over here and the moon is on this side between us and the sun, there's no sunlight hitting the side that we see. Hence it looks dark. But if the moon is over here, then the side we see is completely lit up. Of course, if you look at this picture, you might say, but shouldn't the sun have a shadow cast by the earth that's going like that? And the answer is yes. Yes, it does. But the moon actually orbits about 5 degrees tipped from the plane that the earth orbits around the sun. So most of the time, the moon is above or below the earth's shadow. When the moon comes right through the earth's shadow, then what do we call it? It's going to be a lunar eclipse. When the moon falls in the earth's shadow, it's a lunar eclipse. So what phase does the moon have to be for a lunar eclipse? Full. Because it's got the full sunlight on the side we see, and then it falls into our shadow. They only occur, I think it's there's eclipse season, as we call it, when the moon is crossing the ecliptic, which is the plane the earth is orbiting the sun. And eclipses can only occur in that time frame. And you have a period of a little over 2 weeks when it can happen. And so you can sometimes have both a lunar eclipse and a solar eclipse in the same eclipse season. A solar eclipse is when the sun makes a shadow of the moon that hits the earth. And once again, it can only occur when the moon is on the same plane as the earth is orbiting, so only certain periods of time. But notice the eclipse that's caused by the moon blocking the sun, what we call a solar eclipse, that's just going to be a small region of the earth that's in the shadow. 2017, August of 2017, there will be a full lunar eclipse. And here on Lincoln, we're going to be just on the edge of totality. If you go just like 30 miles south of here, you'll have a complete solar eclipse. So keep that in mind. It'll be like the week before school starts, not next year, but the following year. I was going to have a field trip for astronomy, but school won't have started yet. So, fun things to keep in mind. Do planets have phases like the moon does? Yeah. Yes, they do. Because we have geometry. We could have, if Venus is out here, okay, Venus is not going to be that far away. Now that I think about it, since Venus is closer than the sun, this picture is way off scale, right? I was trying to figure from the moon, it's way beyond where the moon is. Let's just say Venus is out here. Well, the side of Venus that's lit up is the side facing the sun. The side that we see from the earth is this much, and we would see maybe a 3/4 phase for Venus. That was actually one of the observations that Galileo made that further showed that the Catholic idea of the perfection out there and everything going around the sun, starting from Aristotle, couldn't be correct. He saw there were phases for Mercury and Saturn. He also observed the sunspots on the sun, indicating the sun wasn't perfect. He studied the sun using a telescope and his naked eye. Bad for the eye. Okay, you can answer now. And ours depicts a portion of the night sky as shown. Is this possible? This is just a yes or no question, so you should be quick on it. Okay. All right, everybody said no. Why is this impossible? Yeah, we don't have a base on the moon. The moon, of course, continues to go like this. It's just we don't see light from this part because it's not lit up by the sun. It doesn't make it transparent for us to see stars beyond it. This reminds me of something really funny. There is a group based up at Pacific Union College when I was a teacher there. They were making a series of movies on creation. And their first movie, they had a depiction of the Big Bang and the scientific idea of the Big Bang. And so they show basically a blank screen with a few stars, and then all of a sudden, boom, a big explosion. And they had us preview it to, tell them what we thought. And I said, according to the Big Bang theory, there were no stars before the Big Bang. It was empty space, and then there was the Big Bang. And they thought about it, and they wrote me back and said, yeah, you're right, but we're going to leave it that way anyway. I was like, oh, can't do that. I mean, just because I don't believe, doesn't mean I have to depict it incorrectly. Okay, now a quick review for the first exam. First exam is going to be when you get back from your ski break or whatever you're going to do. And so things we need to know. First, the scientific method question will be worth 8 points. And the rest of the test will be worth around 50 points. I haven't made it yet. I don't know exactly how many it'll be. Those 50 points will be split roughly equally from questions in the textbook's question database, which includes, I believe, both true and false and multiple choice. It might be just multiple choice, but I think there's some true and false as well. And then half of it will be from the questions that you guys have written. And you can, when you get them back, if it's got a little red mark down here in the corner, that means that it's going into my database of questions I might use on the test. So you can look at them, and of course they're scanned and on Moodle as well. It's been returned in the boxes out here. And you can see, hey, how many do I have that might be on the test? So that's the composition. Now, that scientific method, very important focus for this class, so I want to go over very carefully so no one is confused about what they're doing when they get to that question on the test. So we start off with, you're going to have to list the 4 steps of the scientific method as we've gone through here. So I have listed here those 4 steps. So you should have, number 1, observe something interesting. Number 2, you create a hypothesis that fulfills these 3 criteria. Number 3, create a test and do the test that will test a prediction of the hypothesis. Your test is not checking to see if your observation was correct. You're testing a prediction of your hypothesis. And then step 4, based on the results of the test, if the test confirms your hypothesis, that is, your test outcome agrees with the prediction of the hypothesis, then you go back and you test differently. But if your test disproves your hypothesis, hey, you know it's wrong. And so then you go back and having this new information, you create a new and better, new and improved hypothesis. Right, you're going to have that process memorized. And then you're going to have a practical application. So I am going to give you an observation. Something like, the sun is lowest in the northern sky on December 21, but late January through early February is coldest on Earth, or coldest in Northern Hemisphere. Not on Earth, because in the south it'd be different. So I give you something like this as an observation. What is step one of the scientific method here? You observe something interesting. So you're going to write this down. Right? It's not that I'm trying to be tricky, but I want to make sure that you actually make that connection that, okay, so this is my observation, so that was step one, making the observation. Then step two, create a hypothesis that explains why this observation occurs, that's based on scientific ideas, and that has testable predictions. So you might remember I talked about, this water spot in the ceiling. It turned out that day or the next day they were working on those problems, and they didn't know about the water that was leaking here, so I had observed it in class and let them know. So I need a test. Well, first I need a hypothesis. Why do you think that it's colder in late January, early February when we're getting the least amount of heating in December? Right? You'll get something and you'll have to come up with your own idea. Right? It's the application of these showing the critical thinking skills. Since no one's answering and we only have 8 minutes left, I will give the actual, as we understand, correct reason. Even though we're receiving more radiation now than we were on December 21, that is, there's more heating coming from the sun, the Earth is still in a net cooling phase. That is, we're still giving off heat at a higher rate than we're receiving it. And somewhere in February, where it starts crossing over and the Earth is receiving more heat than it emits and starts warming back up. So there's a lag because the Earth is still colder than an equilibrium temperature. It doesn't reach equilibrium. Yeah?
Okay, so on the test, I had no idea that answer. So on the test, my hypothesis need to be...
Yours does not have to be correct. That's why I said I'm giving you the scientifically accepted one. But yours has to be something that would explain it and is based on scientific ideas. So this idea is based on the scientific ideas of heating and thermal equilibrium. Right, so you just have to, it doesn't have to be the correct one. I'm not grading it for correct. I'm grading it for thinking. So you have your hypothesis, and then you need to make a prediction of it. So my observation was only of temperatures. I'm not going to go out and measure the temperature every day, because that wouldn't be testing my hypothesis. That would be just retesting to see if my observation was correct. So instead, I'm going to say, okay, according to my theory, the Earth's radiation is greater than the amount that, or the amount of radiation leaving is greater than the amount coming in. I need to have some way to try to measure the radiation from the Earth. And so I'll try to make an experiment, have a satellite out there. Obviously, I can't really do this. Have a satellite out there that measures how much radiation is leaving the Earth and measure how much radiation is coming in so I can see if that prediction or that prediction of the hypothesis was correct. And then for the final, I need to have the outcomes. So for my experiment, if the radiation leaving the Earth in January is bigger than the radiation received in the Northern Hemisphere, then I have confirmed it and I go back and retest a different way. If, on the other hand, the radiation received in the Northern Hemisphere is greater than the radiation emitted, then I was wrong and have to go back to 2. So you need to specify, okay, this outcome I do this, this outcome I do that, one of them being a passing test, one being a failing test. Everybody understand that? It's important to me that you understand it because I don't want people to get to the question and just answer it wrong because they didn't understand what was expected of them. Okay, now the other things in 6 minutes. Know the major subfields of physics. So I listed here mechanics. Everything we have done so far and what we'll be doing in the next section as well is mechanics. Mechanics is looking at, things moving and Dynamics is moving. Statics is stationary, but looking at the forces and how those work on things. Then we go to thermodynamics, talking about heating and temperature type ideas. Electricity and magnetism, optics. We'll cover all of those, and we'll probably cover a little bit of atomic physics in this class. Nuclear physics, radioactive decays and stuff, we will also cover that a little bit. Particle physics, no, we're not going to cover that. And condensed matter physics, well, got to have that there because I got my PhD in solid state physics, which is a subfield of condensed matter physics. So these are the major subfields listed in our textbook for physics. And know what physics is in general. I mean, just a basic question. What is physics?
Understanding of the earth and how it works.
Okay, studying the physical world. Studying the stuff that's really here and how it works. Right, that's what physics is about. And so it covers a lot of different areas, all of these different areas, because they're all parts of our physical world. Yeah.
You're saying we just need to know what each one's about?
Yeah, you should know what each one's about, yeah. Yeah, don't just memorize the list. That's not very useful. Know what each one's about. What about science? What makes something a science?
Study of a particular subject that increases the knowledge. That's
The way you study it is what makes it a science. If it uses the scientific method, that's what makes it a science. Now, I was at a meeting yesterday where somebody typified biology, chemistry, and physics as the hardest science areas. And I was like, by hardest, you just mean the science areas, right? Social science, they do try to use the scientific method. The problem that we over here see with social science is not in the quality of what they're trying to endeavor, but in the fact that they can't control enough variables. It's too nebulous. It doesn't make us over here feel very comfortable. But we consider biology the soft science, just so you know. Yeah. Even biologists will say, yeah, it's the soft science. Okay, you also need to know what our basic units are. So we had mass has its standard unit, the kilogram. Time has a standard unit, the second. Distance, the meter. Force, the Newton, which is kilogram meter per second squared. So you need to be familiar with those. Also make sure you know the prefixes. You know, for this test, I'll make it simple. I'll go from nano to tera. Nano, 10 to the minus 9. Micro, 10 to the minus 6. Milli, 10 to the minus 3. Throw in here centi because we use centimeters a lot. 10 to the minus 2. Kilo, mega, 10 to the 3, 10 to the 6, and tera, 10 to the 9. So just make sure that you have those memorized. So if a question says, which is bigger, a millimeter, a micrometer, or a megameter, you can answer it correctly. Those should be, I think it's in the front cover of the book. Okay, chapter 2, describing motion. Make sure you know what distance is versus displacement, and speed versus velocity, vectors versus non-vectors. Know what acceleration is so you can differentiate between acceleration and velocity, and be able to use those kinematic equations. Now, you're going to have all the equations you need, so you'll have the kinematic equations on an equation sheet. I believe that I have if it's not there, I'll put the equation sheet on Moodle so you can actually look at the equation sheet and know exactly what you're going to have. So if you have been working with an equation, it looks different, so you'll know what it looks like. But you need to be able to use those. Chapter 3, coming in. know how projectiles move, that the vertical motion can be treated completely independently of the horizontal motion. Which direction do you have acceleration? Vertical, because gravity is acting in the vertical direction. So you have the acceleration. If something is flying through the air, freely flying, it has a downward acceleration of 9.8 meters per second squared. Okay, chapter 4 was where we learned Newton's laws. Newton's laws is now what we call dynamics, the reason why things move. So make sure you know Newton's laws, you know the basic forces we've been talking about, and that you can apply Newton's laws to solve problems. Right? There should be a little bit of thinking on the test, and solving problems is where we show that thinking. And then we have chapter 5, circular motion, what we've just finished. Make sure, of course, you know centripetal versus centripetal, what the centripetal acceleration is, so you can use it on something like, swinging the bob around my head. And
You said
Kepler's laws. Huh?
on that last slide, centripetal was on their place.
You are correct, ma'am. Centrifugal is the one that's away from the center. Thank you.
You said there was going to be formula and stuff like that?
Yeah, I'll put the formula sheet on Moodle so you can see it before the test, but it will be there with the test, yes.
But we will have the sheet with us.
It will be stapled to the test, yeah.
Is
Yes,
this
Justin.
during lab or class?
During class.